I grew up in the Midwest where we called it pop. What kind of pop do you want? And then I moved to North Carolina where they call it soda, and further in the South they call it Coke. And here in California most people call it soda. The book uses both words together, soda pop, which, I don't know, doesn't that just sound funny? Would you like some soda pop? Oh, it sounds like you're in the 50s or something. So the slides say soda pop, I'm just going to call it soda. So soda is an example of a gas dissolved in a liquid. The gas is carbon dioxide and the liquid is water. Most liquids actually contain some dissolved gases. Lake water, seawater, the water in your aquarium contain dissolved gases, including oxygen. That's how fish can breathe. There's dissolved oxygen in the water. And if all the oxygen comes out of the water, then the fish die. Your blood contains dissolved gases. There's nitrogen in it and oxygen and carbon dioxide and some other things as well. Even tap water has dissolved gases in it. And water that has dissolved gases in it tends to taste better somehow than water that does not. And so that's why a lot of times on a faucet there'll be an aerator. What does the aerator do? It mixes air with the water as the water comes out and makes sure that the water has plenty of dissolved gases in it. So the solubility of gases in liquids does not increase with increasing temperature. It decreases. So think about warm soda versus cold soda. Which one fizzes more crazy when you pour it? Warm soda. You left a 2-liter bottle of soda in your car in the summer, and you pick it up, it's like, man, this is hot, I'm pouring this on some ice. This fizzes all over the place. Because the solubility of carbon dioxide in warm soda is very, very low. It's higher in ice-cold soda. And you can, think about this. If you had 2 cups of soda on a counter, and one was warm and one had ice in it and was nice and cold, which one's going to go flat faster? The warm one, right? You could try that one at home too. It's opposite with solids. And you can think about putting sugar into tea. I lived in North Carolina, and there they drink a lot of tea, and there's 2 kinds. There's sweet and unsweet. And the sweet tea is very sweet. It's not sweetened, it's sweet. Sweet tea or unsweet? Well, if you've got iced tea, and around here, if you order iced tea, it generally doesn't have any sugar in it, does it? That's what they would call unsweet. So you got iced tea, it's ice cold because it's got ice in it. And you like yours sweet, and so you pour some packets of sugar in there and try to get it to dissolve. It takes a long time, doesn't it? The sugar is less soluble in cold water, and it takes a longer time for it to dissolve. Whereas if you pour sugar into steaming hot tea, it dissolves very quickly, doesn't it? So that can help you remember these trends. That solids are more soluble at high temperatures, gases are less soluble at high temperatures. Here's another thing you can try at home. Take some tap water and heat it on the stove and watch it. They say a watched pot never boils. It's not true. You just get tired of watching it. But if you heat ordinary tap water on the stove and watch it, you'll see that long before it starts boiling, there's these little tiny bubbles that start coming out. Is that like pre-boiling or something? No. There's dissolved air in the water. And as you heat it up, the solubility goes down and that dissolved air comes out of solution. It doesn't precipitate and make a solid at the bottom because it's a gas. It makes bubbles and it comes up to the top. So you'll initially see these little tiny bubbles forming, and then you'll see nothing for a while, and then it will start to boil. You could also do that with a beaker in lab this afternoon if you wanted to. The solubility of gases depends on temperature. It also depends on pressure. Henry's law states that the higher the pressure of a gas above a liquid, the more soluble the gas is in that liquid. So let's look at this illustration. So here we have a liquid with dissolved red gas molecules. I don't know what these are supposed to be, but they're red gas molecules. So the gas molecules are flying around up here, like gas molecules do, and some of them crash into the water. And then they become dissolved in the water. And some of these guys will come to the surface and escape. So it's a lot like that condensation evaporation equilibrium we talked about. But here we're not looking at the liquid molecules. We're looking at a solute that's dissolving in the liquid and coming back out. So there's an equilibrium. What happens to the equilibrium if we put a whole bunch more gas particles up here? We're now increasing the rate at which they're going into the liquid, right? And it's going to take a while before the rate of the gas particles leaving the liquid comes up to match it, because the dynamic equilibrium you've got going in both directions at the same rate. And so the net effect is that when you have more gas particles up here, you will also have more gas particles dissolved in the liquid. So this is happening in a can of soda. So here's your can of soda. There's always a little headspace here. Looks like air, but it's not. It's carbon dioxide. It's under pressure, and that's why there's that wonderful psh sound when you open the can. That's the pressure escaping. So here you have pressure of carbon dioxide above the water. The water, has all kinds of other things in it too, like caffeine. Caffeine is fun. So the carbon dioxide is dissolved. When you release that pressure, now the solubility of this goes down, and we see the gas coming out. Before, the gas was coming out and going in, but now we're releasing this gas. These gas particles can fly away. Once they get out of the can, they're not going to come back and go back into solution. They're going off on some adventure. Probably get taken in by a plant or something and turned into oxygen. Any questions about that?